When dealing with arcs and chords, I feel like all these theorems and properties that we have with them really make sense. When we get into our secants and tangents, those ones, there might be some rules and some theorems that we actually have to memorize, and they kind of make sense, but they're not quite as straightforward as the ones we have here. For example, our first one, it says in the same circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So for example, here looking in this circle, if F, G, and JH would happen to be congruent, then I know the measures of their arcs would be congruent. So this arc would be congruent to that arc. FG would be congruent to JH, right? Because they kind of match up, right, with those endpoints. So it makes sense. Let's just look at an example here. In the figure, circle A is congruent to circle B, and WX is congruent to YZ, the arcs. Find WX. Well, we know that WX, the arc WX right here, boom, is congruent to the arc WZ. So that means their chords are also congruent. Well, if YZ is 14 centimeters, then WX also has to be 14 centimeters. Pretty straightforward. Couple more here. Theorem 10.3. If a diameter or radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. So basically right here, we're showing that a diameter or a radius, so either one, the diameter or the radius, if it bisects a chord, which it does right here, or not bisect, if it's perpendicular to a chord, which we're showing right here, then it means it bisects that chord and its arc. So what does it mean to bisect? Well, it cuts it right in half. So we know that XZ and YZ would be congruent. We also know that these two arcs, XB and BY, would also be congruent to each other because it bisects that arc. Okay, so as long as there's a perpendicular with the diameter or a radius and a chord, it bisects that chord and that arc that the chord makes up. Also, the perpendicular bisector of a chord is a diameter of the circle. So basically, if there is a perpendicular bisector of a chord, then we know that the thing that's perpendicular to it, that's bisecting it, is a diameter or a radius. Okay, so it's almost like the vice versa of 10.3. Let's do an example here. It says, in circle G, the measure of arc DEF is 150 degrees. So remember, we're thinking from D to E to F, that whole thing is 150 degrees. Find the measure of arc DE. Well, if we take a look, we have a perpendicular of the radius and a chord, which that was just our last theorem. If there's a perpendicular between the radius and the chord, we know that it bisects. So I know that these two chords are congruent, or the two parts of the chord are congruent. So I know this part would also be 5. And the arcs would also be congruent. So I know that these two arcs would also be congruent, simply because of this perpendicular right here between the radius and the chord. Well, that basically just cuts this 150 in half for each of these little arcs. So we cut this in half, so I know that the measure of arc DE is 75 degrees. So this piece right here, 75 degrees, because the other piece would also be 75 degrees. Another theorem, 10.5, it says, in the same circle or in congruent circles, so same type of thing, two chords are congruent if and only if they're equidistant from the center. So make sure, equidistant means the same distance, but you also got to remember that the same distance, that we're considering the shortest route possible. And when we consider the shortest route, we're talking about the perpendicular route. So in this case right here, in my circle, so each of these chords, to see if they're equidistant, that means the line that makes a perpendicular to that chord, right? We see that little perpendicular? The line that makes a perpendicular to that chord. So we're saying that those two would be equal if the chords are congruent. So if I'm saying that FG is congruent to JH, boom, boom, then they would be equidistant from the center. But you just got to make sure that it's the distance, the perpendicular distance. And you'll see that in your pictures here. Let's try one. So it says in circle P, EF and GH are both 24. Let's write that. So EF over here is 24, GH is 24. So that means they're congruent. I'm going to write that. So EF we know is congruent to GH, those two chords. Find PQ. Well, if those two are congruent, what did we just talk about? That they would be equidistant from the center. Well, here's the center. We make the perpendiculars. So that means these two guys would be equidistant, the two chords. So I could set 4x minus 3 equal to 2x plus 3. And then we just go through our algebra and solve. So we get our x's to one side. And we're left with 2x. Bring down the minus 3 equals, gone. Plus 3, I don't need my plus sign. 3. And then we add 3 over, add 3. So it looks like we got 2x equals 6. And divide by 2. And x equals 3. So I didn't even really need that information that EF and GH were 24. Besides the fact that I needed to know that they were congruent, first of all, in order to say that those segments were equidistant. So x equals 3. Lastly, this is where it gets a little trickier. This is where you really got to look closely and use information that you know. It says in circle C, diameter AB is 18 inches. So I'm just going to write this down. D, the diameter is 18 inches. I like to just write down information I know. I know the radius is 9 inches. I might have to deal with the circumference. Who knows? Okay. And it says, and chord EF is 8 inches. Find CD. So we're trying to find this piece right there. Find CD. Well, it had to have gave me this 8 inches for a reason. So EF, that chord is 8 inches. What do we notice? With the diameter here, it makes a perpendicular with that chord. So we know that it bisects the chord. That diameter bisects the chord. So I know that these two guys are congruent. Well, if it's 8 inches all the way across, that means each piece is 4. So I know that this distance is 4 right here. Well, how the heck am I going to find CD? I know that CB, I know that that radius all the way across is 9. But do I know what DB is? Do I know what that little piece is? I'm not sure what that is. I can't find it. All right, so let's keep looking here. So I know that ED right here is 4. And we're trying to find what CD is. Well, this is where you got to look closely. And this is where the tough part comes into play. I said the radius is 9 inches. So that means I could draw any radius on this circle I want to. I can go like from here to here. I know that's 9 inches because it's a radius. Well, if I take a look at the two sides that I've drawn in so far. I have that we know this is 4. We know ED is 4. We're trying to find this. Well, what happens if I happen to make a right triangle right here and connect C to E? Do I know what that distance is? Yeah, it's the radius. I know that's 9 inches. And I just made myself a right triangle. Well, if I know two sides of a right triangle, I can always find the third side. So let's just call this guy x. If I want to find x, I can use the Pythagorean theorem, right? A squared plus b squared equals c squared. And in this case, we know the c is 9 because that's the hypotenuse. And so we got x squared plus 4 squared equal to 9 squared. And this will fly through the algebra here. So we got plus 16 equals 81 and subtract 16 over. So x squared equals 65. So we're taking the square root of 65. And if we look at our directions, it says round to the nearest hundredth. So we'll go ahead. It should be 8 point something. So the square root of 65 gives us about 8.062, so 0.6. And really we found what CD was. Instead of putting X, I'm just going to write CD equals 8.06. And we have a label, so we better write inches behind it. There you go. So like I said, sometimes you got to look very closely. And in that case, we had to draw in that radius there. Okay, so you might use some other information, right? So don't be surprised if that happens.